We're still talking about the streaming of stored multimedia content, and we talked about this example of constant bitrate video, and we said that this is the evolution of the data with respect to time for constant bitrate video. And due to the network delay, we have some variable delay where these packets will arrive at the client side. So if we were to delay the play out time to something like this, for example, we can just have some problem of these packets. So even though these packets will arrive to the receiver, but they will arrive later than the play out time, in which case we need to compensate for this. So in that case, we need to have a play out time of, this is of course given that we have some buffering, some de-jitter buffer. So if we delay it further down, so in that case, when we start playing out, it would be, we will not lose any packets during the play out time. So of course, as we have studied before, the jitter is actually this time. So for those two consecutive packets, that's the jitter, and this is the jitter, and so on. So we can calculate, of course, the average jitter, or the maximum jitter, or the median jitter, or something like this. So throughout the time, we can calculate the difference in terms of absolute delay between any two consecutive packets, and based on that, we can get some statistics on how the jitter behaves, which will affect the design of the de-jitter buffer at the receiver side. So the de-jitter buffer has a certain size. So this size, so the size here is affected by two things: by the expected rate of filling that, and the variation in jitter. So if that variation is really wide, okay, then we need more jitter, because in that case we need to account for the fact that there might be some long jitter or long delay difference between two consecutive packets. So in that case, we need to delay the play out time of that delayed packet until it actually arrives to the buffer. So in that case, we need a longer de-jitter buffer at the client side. So the question is now, what do you think is this buffer size as a function of the protocol that we use on the transport layer? So UDP versus TCP. So what do you think in terms of this buffer size? On average, will UDP require longer buffer size, or TCP requires longer buffer size? TCP, why?
Because it has to wait for packets. Because it should receive all the packets, and if the packet is lost, it will wait till it's been transmitted. So it will have a longer.
That's one factor. The other factor is the congestion control on the TCP level. By congestion control, we mean that if there is any packet loss, UDP will not care. UDP will not do anything specific. But TCP will do what? Will drop, no. Congestion control. Not packet loss. It will drop the rate.
Yeah.
So it will keep dropping the rate and then increasing the rate, dropping the rate and then increasing the rate. So the variation in this rate, okay, affects the jitter. So you will have longer range in terms of jitter. So this variation of delay will affect the variation in jitter. So you will have a maximum jitter which is longer compared to UDP. UDP will not do anything specific. So assuming that the network will not add any effect for UDP, the rate at the receiver side will almost be constant, assuming that the network is functioning correctly. So in that case, the jitter will not change drastically for UDP. But for TCP will try to push the network to the limit, and if there is any packet drop from the network point of view, it will drop the rate, and then it will increase the rate, and then drop the rate. And then, so this variation creates some variation in the jitter values, which requires some longer buffer in order to smooth out this variation in rate. Okay, so we'll mention this again later. So in which case, if we try UDP, if we assume that we have again this scenario of constant bitrate video, if the server sends a rate appropriate for the client, assuming that the generation of the multimedia content at the sender side is appropriate for the client, so the send rate will be equal to the encoding rate, which means that when the sender sends a packet, okay, with a constant rate, the transmission rate will be equal to that encoding rate, right? So when the packet gets generated, when the video content gets generated at the sender, it will be sent to the network at more or less the same time, because UDP will not do anything special. Unlike TCP will look at the network first to see if the network is congested or something. Then it will take the packets from the encoder, and it may actually drop the rate or increase the rate or something like this, right? So TCP will perform flow control and congestion control, which means that it might adapt this rate from the encoder based on the network state. مفهومة دي؟ So TCP will take the packets from the TCP buffer, and then it has to look at the network. If there is any packet loss from the network side, then it will drop the rate. If there is no packet loss, it may actually increase the rate. So it will make the rate variable. UDP will not do anything. Once the packet becomes available from the sender side, it will send it at the exact same time. It doesn't do anything special, okay? Which means that for UDP, the transmission rate is equal to the encoding rate. Once the packet gets generated, it will be sent. Okay? Again, we'll just explain it. So this is the sender. This is the encoder. Okay? And this is UDP. Okay? So the encoder will send one packet to UDP. Okay? In that case, in the UDP socket, UDP will send it once it becomes available. It doesn't do anything specific. Right? So in that case, the encoding rate equals to the transmission rate or the sending rate. Right? Because once the packet becomes available from the encoder, UDP will send it. Will not do anything special, because UDP is dumb. It doesn't think. Okay? For the case of so in that case, this is equal. For the case of TCP, however, so this is the encoder and this is TCP. So the encoding rate and this is the transmission rate. Once the packet becomes available, TCP will first look at the network. So if the network has any congestion or if there is any one packet loss, and this is particularly critical for the case of, for example, wireless. Sometimes there is one packet loss from on wireless due to channel fading or something like this, or obstacles or something like this. But the network is not congested. So in that case, TCP will be deceived and will drop the transmission rate, maybe making the encoder rate more than the transmission rate in some cases. And in some other cases, it may be actually longer, or greater than the rate. Okay? So TCP will actually create some variation in rate. Sometimes this variation in rate is good in the sense that if the network is congested, I have to lower the rate. So that's true, right? So it actually senses the network, and based on the network state, it will drop the rate. That's what it should do. In fact, if there is a network congestion, for the case of UDP will congest the network, will send all the packets. So in that case, the throughput, the receiver rate will be much less than the sender rate. And in that case, you will have a problem at the receiver. But as far as UDP is concerned, doesn't care. It will congest the network. It will send everything to the network without anything special. UDP tries to adjust the receiver rate close to the transmission rate. Okay? So if the network is congested, it will try to lower the transmission rate to adapt to the network state. Okay? So in that case, for UDP, the transmission rate is equal to the encoding rate, which is in that case constant bit rate. Okay? So assuming that the network is working fine, which means that the receiver rate is good. Okay? The receiver rate is good. So the network state is okay. So in that case, the play out delay or the jitter will be sort of fixed. Yes, bravo عليك. Sort of fixed, which is actually proportional to the encoding rate only. So the network did not do anything weird in the multimedia content, because the network state is good and the encoding rate equals to the sending rate. So they will arrive almost in a constant bit rate, which means that the play out delay, which is the jitter or the consecutive delay between multiple packets, is actually more or less fixed, and it's function of the original video. So it will be very much contained, and in that case, the buffer size at the receiver, again this assumes that the network state is good. Okay? Consistently good. Okay? So in that case, the receiver side will not require long buffer size, because the jitter is almost fixed and it's reasonable, so the buffer size required is pretty small. Okay? Versus for TCP, so the TCP tries to send at maximum rate. So it tries to actually push all the packets as much as the network can handle. And then, if it finds any problem in the network, then it actually drops the rate sometimes to half, and then it goes up, and then it goes down, and then it goes up. So in that case, the transmission time fluctuates. Okay, so that creates, and this fluctuation is due to congestion control, TCP congestion control. So UDP does not have any congestion control or flow control or anything. Okay, so this actually requires large play-out delays at the receiver side, because the packets may arrive in shorter delay or longer delay. So, but the difference may be actually very long or very short, depending on how TCP finds the network. Sometimes TCP gets deceived easily. Okay, and this particularly happens in the case of wireless. And that's why in the second part of the course we'll focus on wireless, because wireless is the most challenging in everything. So sometimes the network in wireless can drop one single packet due to instant failing, but then it goes back to normal very fast. Okay, but TCP will not cope with this. It will drop the rate to half, and then it will increase it slightly, slowly. Okay, because TCP originally was designed for wired network, not wireless networks. Okay, so in that case, we need large play-out delay and typically longer buffer size to smooth out the variation in jitter for TCP. But again, buffer is cheap. For us, buffer is cheap, and that's why we can still handle streaming over TCP if we are careful in choosing the buffer size. Okay, and that's why until today, TCP still dominates the streaming servers because of the fact that HTTP uses TCP underneath, and HTTP is very much attractive to all the multimedia content providers because it can pass through firewalls and it has some other benefits which can be attractive for the case of TCP. Okay? Any questions?
The encoding rate will be regardless if it's compressed video.
No, the encoding rate. Of course, the encoding rate depends on whether you use uncompressed or compressed. For the case of uncompressed, basically the encoder is PCM or parse code modulation. So it just gets the audio or the video content and generates samples. That's it. So it doesn't do anything special. It actually converts the analog voice or the analog video signal into samples. And then it transmits the samples as is. It doesn't do any compression. So the encoder in that case will have a fixed rate. Okay? For the case of compressed audio or video, then we use, like, for example, JPEG or MPEG or something like this. So it depends on how the video, it depends how the scene looks like. You may be able to compress more or compress less, and in that case, the encoding rate will change over time. Okay? But still, in both cases, UDP will not care. Once the packet becomes available, it will send it. So the encoding rate, again, matches the sending rate. There's no modification or there is no adaptation in between. TCP will not do that. Okay? All right, so typically on the internet, we have another factor of variation which we need to account for. And this is the fact that the potential clients may have different capabilities. So some clients may have high speed connection through, like, for example, fiber optics. Someone has a plan of 10 megabits per second versus another one who has 1 megabits per second or something like this. Or in the past, of course, we're lucky today we don't have this, but in the past we used to have dial-up, which gives you a rate of 28.8 kilobits per second, which is a joke now, but 2 years back, this was the case. So we have potentially clients with different capabilities. So you have one client with a high definition TV and very strong connection, and the capabilities on the client side allows that client to be able to receive high quality content. So in that case, we need high data rates, okay? And for other clients, poor clients with dial-up connection, we need lower quality. So how can the server account for this? There are two ways here in the book. There is one way mentioned, although there are some other techniques for this. So the server will commonly store multiple copies of the same video. Okay? And that's what typically happens on YouTube. So when we watch the video, sometimes it's set to auto, right? On the client side, it's set to auto, which means that the client will sense your connection. And if it finds that your connection has low data rates, then it lowers the quality of the video automatically. But you can change it manually to say that, well, I have high-speed connection, so please send me the high-quality video, or a low-speed connection, which means send the low-quality video. So in that case, the server So this is the straightforward approach. The server will store multiple separate copies of the video. Nowadays, we're talking about more complicated type of video streaming or streaming servers, which can store one copy of the video ultimately, but with variable adaptive encoding. So the video itself, inside it, will have layers. So it's one copy of the video, but it has layers. And these layers will be sent to the users depending on their capabilities. So it's one copy. So if we have high definition TV, we'll have all the layers. So, and automatically, the network, using some quality of service, will drop some of these layers depending on the capabilities of the client. Okay? This technique or this method, by the way, is not mentioned in the book. Therefore, you're not really required to know details about it, but it's there. So the content distribution servers nowadays, they account for this. They have what they call adaptive video encoding. So the video is actually encoded in terms of layers, and if you have all the layers, you have the highest quality. If you have a lower capability connections, maybe you get 2 layers or 3 layers, but not all the layers and stuff. So in that case, you can actually use even multicast, and instead of having separate connections where you transfer the multimedia content here and here, because here the rates required is actually 1 megabits per second plus 28.8, right? If I have adaptive video coding, then I can send one session to multiple receivers, and this router will be intelligent enough to recognize that this guy is poor, so I need to drop the higher layer. And in that case, the rate will be maximum 1.5 megabits per second. So this rate will not be added to the network, which is, in that case, another type of bandwidth management from the network point of view. But the network has to account for this, okay? And it has to communicate with the streaming server and things like that, okay? But again, this is not, you don't need to know the details of this. Okay, so as we said before, RTP and RTCP, they have some packet sequencing, and they can sort of account for the fact that the server will stop streaming the packets because we have packet sequencing and we have timestamps. So if the packet sequence stops at sequence 2, and then we get sequence 3 after 5 seconds or 20 seconds or something, we will know that this is the continuation of the same video. So this pause will, from the server side, will be accounted for using RTP and RTCP. So that's given. But what if the client itself wants to pause the video or wants to play the video from a certain position, or which is what we typically do over on YouTube or something? First of all, HTTP does not handle this, does not inherently have some commands for the user to interact with the server. So either the developer has to create that protocol over HTTP as part of the application layer, or we can use what we call real-time streaming protocol. RTSP, which is defined in this RFC, and I'm really terrible in memorizing the numbers of RFC because I never thought it's important in any way. So RTSP is an application level protocol, okay, which is used to facilitate the interaction between a client and a streaming server. Okay? So that's the actual definition of RTSP. So it actually accounts for the control from the client to the server to rewind a video or audio, or to pause, or to fast forward, or to play from a certain position, or something like this. So when we interact with the stored video, and I stick on the words stored video, because there is another level of interactivity where you have IP telephony or something. That's a live interaction between two people. But here we're talking about an interaction between a client and a server. Okay. So RTCP is the way to go. So what RTCP doesn't do is to it doesn't define how the audio and video is encapsulated. It's not a data plane. It doesn't deal with the data itself. Okay? It facilitates only interaction between the client and the server. It doesn't restrict how the streamed media is transported. So it's agnostic to whether you use UDP or TCP. It doesn't care. It's isolated and separate from the type of the transport protocol that you use for streaming. Okay? So it doesn't restrict that RTCP has to work with UDP or has to work with TCP. It doesn't care. Okay? It doesn't specify how the media player buffers the audio or video. So it doesn't have anything to do with that. So whether you use digital buffer, what's the length of the buffer, these characteristics of the media player or at the server or at the client, it doesn't actually care about this. Okay. So all it does is that it actually facilitates the interaction between the client and the server. So when do you want to play? When you click on play, then you send an RTSP command to the server to start streaming the packets. When you want to pause, then RTSP will send a command to the server to stop the packets, which means that if you use RTP over UDP, the streaming server will stop, in which case the packet sequencing, if you start again, the packet sequencing will continue. Okay? Or if you want to reposition, which means that you want to start playing from a different position, then the RTSP command will inform the server play from a particular position. Okay? So that's basically what it does. In the book, it tries to draw some analogy between RTSP and FTP, although I don't find this really relevant to the context. But the way that it positions this analogy is the fact that FTP, if you remember from 455, it uses out-of-band control, which means that we have two different ports, two different sessions, one for sending the files and one for the control, how to set up the FTP session, tear down the FTP session, or get or put the file and stuff like that. So it tries to position RTSP as the control session of the stream. Okay? So in a way it's analogy, although there is some big difference between the two. So similar to FTP, that it uses out-of-band control, RTSP is sometimes referred to as the out-of-band streaming control protocol, okay? Because it uses a separate port or session. So if you remember the third scenario that we talked about last time, we said that we use HTTP to get the Metafile content, right? And then we use a separate streaming server where we can connect to this streaming server either using UDP or TCP, okay? Because the web server is separate from the streaming server. So in which case it allows us to connect to the streaming server using UDP or TCP. We'll have the flexibility in that case. So for connecting to the streaming server, we need to have actually two connections. One will use a port for streaming the multimedia content using UDP or TCP, and another one for RTSP. which in that case, it uses a separate port for out-of-band control of how to stream that video or audio. And the control here is basically for facilitating the interaction between the client and the server. Okay? So in that case, the media stream itself, so streaming the content, is what we call in-band. So in-band, we refer to the data or the multimedia content. And out-of-band, we refer to the control. Okay? So, as an example, so we have a scenario where, again, we need to send a metafile, and again, the metafile is the file that describes the multimedia content, whether this multimedia content is composed of audio or audio and video, what is the encoding on the audio, what is the encoding of the video, and so on. So in that case, HTTP will initially be used to get the metafile. Okay? After we get the metafile, then we will have the flexibility to connect to the streaming server, which doesn't have to be through HTTP. It could be directly using TCP or UDP or RTP over UDP. Okay? And in that case, we need to connect to the streaming server to get the content of the multimedia, and we need to set up a separate session for RTSP, okay, to facilitate the control or the interaction of how we play this multimedia content. So that's the sequence. So that's the sequence of how we connect. So this is the typical sequence on YouTube. How we connect to the HTTP server first to get the metafile. Okay. So the metafile that we have seen in the previous slide will get downloaded to the client web server. Okay. Web browser, sorry. So the web client will fetch the metafile. From the metafile, it knows now that it has 2 copies of audio. It has 1 copy of video. So it needs to set up the session with the streaming server, okay? And so that setups the RTSP session to control the streaming of that audio video content. So this setup will set up the session, okay? And then the client will say play. So when it clicks on play, it sends this command to the media server, and the media server will then start. Of course, it has to respond first It has to acknowledge the fact that it accepts that command. And then it starts streaming the audio-video content. Okay? So that's the data part. And this data part could be using a TCP or RTP over UDP. So, RTCP itself does not dictate how the media will be streamed in terms of transport layer protocol. Okay?
I'm very confused between RTSP and RTCP.
No, RTCP is the control protocol that works with RTP. So when we say the word RTP, we assume that it's RTP, RTCP مع بعض. يعني هم they work hand in hand. So when we say RTP, it has to have RTCP. Okay? Both of them, they work typically over UDP to facilitate زي ما قلنا, to facilitate بقى اللي هو packet sequencing, time stamping, and so on and so forth. Okay?
Doctor, would it be beneficial if we use the RTSP for real-time data streaming?
Yes.
From an IMT
Well,
server?
from the whether it's real time or not real time, RTSP, it doesn't. Even though it's called real time streaming protocol, that's what it's typically used for. But RTSP itself doesn't care whether you are doing streaming or not streaming. Okay. This is where you control whether you want to download the entire content and then play it, or pipelining, which means that as you download, you play, which means that it's real time.
But
Okay.
it could be used for data.
It could be used for data, yes. And typically it could be used for data. So you want to download the data and then say pause if you want to do this. If there is any application for doing this, you can typically use RTSP. Okay? Any other questions? So
Using TCP also will use RTCP or TCP control?
no, TCP on a TCP itself, typically RTP is used over UDP. So RTP is used over UDP. Okay? TCP is separate.
So the media streaming using TCP in the setup also will use RTCP?
No. RTCP has to come with RTP. RTCP is the control protocol for RTP. They have to come together. They cannot work without each other.
So the setup will use the TCP control?
RTSP.
The setup here is for RTSP. Okay?
In case using the data, transfer the data using the TCP?
And UDP.
No, and UDP, it doesn't care. As we said, RTSP is agnostic to whatever transport layer protocol you use. And the two possibilities for us are actually, you can say three possibilities. We have UDP, we have TCP, we have RTP over UDP. These are typically it can be used for any combination, doesn't care. It doesn't care, okay? It can be used with any of them. Okay, or even a fourth transport protocol if you want to use, I don't know, TCRP or something like this. Another transport layer protocol. Doesn't care, okay? It doesn't have anything to do with it. If the user in the middle of the play, assuming that it's real-time streaming, if the user wants to interact, then the user might click on pause, in which case RTSP will send a pause. It's a text-based command. It's very simple, as you will see. We'll send a pause command to the streaming server. In that case, the streaming server will stop. It would be nice in that case if you use RTP, because RTP will handle this nicely in terms of it will stop the packet sequencing, and then the timestamp will be increased by when you say play, then the client will nicely get the continuation of the packet sequencing with the proper timestamp. So you know that this duration has been silent. Or if you want to finish everything, then you say tear down. So this is the sequence in terms of commands from RTSP, okay, to the server and the response back. So basically, it's a request response, in a way similar to HTTP, okay. As we said, it's text-based. So first, we set up an RTSP session, and we say that the transport layer protocol is RTP over UDP. This could be TCP. It's perfectly fine. And whether we're using compression or we're not using compression, and this is the port number, which should be different from the session or the socket port for UDP. So that port is the port for RTSP, not the port for UDP. Okay, port for UDP is different. Assuming that the server will accept this, so the server will acknowledge, which means that it's okay to set up the session on for RTSP, and then the client will say play. Okay, so when you click on play, then it will send that command play. Okay, on the same RTSP session using this URI or URL, and then you say range 0 to whatever, which means that you want to play from position 0. Okay, so that's the range. We want to play from position 0, because in some cases you want to watch a video on YouTube, but you want to watch it from a particular position. So in that case, if you click the cursor in the middle of the video and say play, in that case this 0 will be different. Maybe you want to play it from second number 100. Second number 200 or something like this. So this will be 200 dash or 300 dash. Okay, so this will send the streaming server the command to start streaming from that particular position. And because the stored video has some timestamps inside the video content itself, so the streaming server will know exactly where to start from. Okay. Then, if the client say pause, then it will again send the pause command. So it's all text based, and then at the end you say tear down. So that's client server, client server, client server. So it's always based on request response type of command. And as you can see, it's text based. It's very simple, and you specify the URL to identify the RTSP session that you want to send this command over. Okay?
Can you the RTSP will know where to start because the timestamp from the RTP, right?
Right.
But if we are not using RTP, how do you know?
It's up to well, if you're not using RTP, you're using TCP.
Yeah.
Okay? So TCP, the streaming server will also stop. Will also stop streaming. Okay, TCP itself does not deal with timestamps. Okay, so it's up to you to synchronize the audio with the video. So you have to have a way to synchronize, for example, audio with the video. So in that case, the player at the client side will have another technique, maybe similar to RTP, to synchronize the audio with the video. Because TCP itself does not provide timestamping. It provides packet sequencing, right? So TCP has packet sequencing. So from that perspective, you will get the proper packet sequence. But timestamping will be your responsibility at the client side. Okay?
The pause on the TCP, so just send the sequence number.
Sorry?
In case
of TCP.
Yeah.
Yes. So I will recognize from the sequence number that this is a continuation of the file, but I will not get the timestamp. In which case, synchronization between audio and video will be my responsibility at the client side. Okay, so we'll stop here.